Yeah, so I just want to talk about like this Ramanujan's tau function and congruences, and mainly talk about congruences of modular forms. Uh, and since it's the National Mathematics Day and it's Ramanujan's birthday, I thought it's a good topic to start off with. So, so first, so Ramanujan defined the tau function as the coefficients of this Q expansion. So Q expansion is just like a power series in Q, and then the power series Ramanujan was interested in is this intriguing like special power series which is Q, and you have this infinite product of 1 minus Q to the n to the power of 24, and n is from 1 to infinity. As so here we can just look at Q as an indeterminate, and so this will be a one variable power series. So, and when we expand this out, we'll have these coefficients of Q to the n, which are defined as the tau function, the values of the tau function, tau n, and they're all integers because of the product itself. So the
Okay. Mm.
so Ramanujan was interested in this. We'll see later because the left-hand side actually comes from something called as a modular form, and that's why the right-hand side, the coefficients tau n are pretty interesting. So he made some conjectures which are only for this tau function, which are called as the Ramanujan conjectures. But these are also have been generalized and proved for like generalized some special modular forms. Uh, so the for the tau function tau, which is a function on the natural numbers, and it gives us an integer. So Ramanujan conjectured the following. Um, so it is a tau of nm is tau of n times tau of m for n comma n coprime. So when I have two integers n comma m which are relatively coprime, so no prime, they don't have any common prime factors, then tau should be multiplicative. So such a function is called as a multiplicative function. So this means that the values of tau um, at any integer can be known if you know the values of tau at prime powers, and that follows from the fact that from the fundamental theorem of arithmetic, where every integer can be written as so if I take any n, it's be the n1, p1, n1, pk, nk. So when so now tau of n is tau of p1, n1, tau of pk, nk, because of the multiplicative property, the conjecture multiplicative property. And the second one talks about the prime powers themselves. I should have mentioned that p is a prime in 2, where tau of p to the n plus 1 is tau of p times tau of p to the n minus some scalar p to the 11. So this 11 is, we'll see why 11. We'll see it's because it's 12 minus 1. And 12 is, we'll see 12 because it'll be the weight of certain modular form. But in 2, tau of this equation in 2 just gives you a recurrence relation between value of tau of p to tau of p squared to tau of p cubed, so on. So you only need to know tau of p for every prime. So these
So
two,
this is a very special arithmetic function.
yeah.
Tau, yeah.
So these two implies only need to know tau of p for p prime. So if you know the value of tau at primes, you know the value of tau everywhere else. And for primes itself, Ramanujan conjectured a bound, or it should be not equal to, it should be less than or equal to here. It should be at least at most 2 to the p to the 2 times p to the 11 over 2. And it won't be equal to because 2 to the p to the 11 over 2 is not an integer, so it will be strictly less than. So that is So the first two is pretty uh, neat. So I can just um, say that. So for the first two, one uses the theory of model forms and Heck operator to show or to prove the first two things. And the third conjecture is very non-trivial and it is a theorem of Deligne, and it is his proof of the wave conjectures, uh, which is highly geometric, proved the third part of the Ramanujan conjecture. So the first two are pretty straightforward when you know the theory of model forms and Heck operators. Uh, Heck operators are okay. I'll come back to them later if I need to, but
But Aniruddha, if you are
yeah.
connecting them to Weyl conjectures, then that's something like Diophantine properties, right?
Yeah, I'm actually not sure the exact connection of this to the wave conjectures themselves, but it is said that the proof of Deligne's proof of the Riemann hypothesis for the wave conjectures.
Over
So wave
finite
conjectures
fields.
is or
Riemann
finite fields,
hypothesis is
yeah,
over finite
or
fields.
finite fields, yeah. That implies this thing.
Okay.
So I forget how I don't think I specifically know how that implication follows. Okay. So one other important conjecture is about these tau n, which is currently also open, is the fact that tau n does not vanish, and this conjecture is known to hold for large n. Um, but and this so to prove this conjecture, people study like so if you want to show something is zero or something is non-zero, it is easier to look at modulo some primes because it's an integer and show something there. So that's one motivation to like look at um, the values of these tau n's modulo certain prime, and that's where the congruences come into picture. So one interesting congruence which Ramanujan showed was the following. So he showed that tau n is congruent to sigma 11 n. So where sigma 11 n is the sum of the divisors to the raised to the 11 of n. So I'm looking at a specific integer n. I'm looking at its divisors and taking the power 11th power of these divisors d, and then taking sum of all of these. And see here, even again, like there's 11 here, we'll see why the 11 is coming up. Um, but the congruence is a modulo 691, and even this is something special as well. And so now Ramanujan proved this, uh, I guess, not using what we like, not using the modern techniques of showing like two modular forms are congruent modulo a prime. So that's what I'll be trying to motivate. So one should vaguely think of this as so tau n's they come from geometry in the sense that so these modular forms or cusp forms, which I'll talk about, are more geometric in nature, and these sigma 11 they are pretty close to number theory. So this congruence is giving you some bridge between geometry and number theory. So that's one way to look at this. And the aim of this talk is just prove this congruence and say why 691 is special in this case.
Yeah.
Is that fine? Yeah. Okay. So first, let's introduce what are modular forms. So we look at the main thing we want to look at is the complex upper half plane in this case. So it is all the complex numbers x plus iy, with Y positive. So it is this part. And SL2R is a 2 cross 2 real matrices with determinant 1. And this group acts on the above plane by taking ABCD as a matrix in SL2R, and acting on Z is by the Möbius transformation AZ plus B over CZ plus D. And so this belongs to the upper plane since uh, determinant of gamma is 1, which is strictly positive. So we can, so since 1 is positive, like it'll preserve the upper half plane. Otherwise, it'll take the reflection. But we are only interested in SL2R. Moreover, this action is not so good. It'll have a lot of fixed points and stuff. So we want to look at an action of a discrete subgroup. So that's usually what people what people do. So I'm going to come back to that later. So we'll be interested instead of SL2R, we'll be interested in SL2Z. So this is bad and this is good. So we'll be interested in that. So for a modular form is a holomorphic for function f on the upper half plane to C, and it is said to be of weight k. It's a modular form of weight k if we have these two following properties. So if I look at gamma A B C D for SL2 Z, I should have written Z here. So I'm looking at the action of the discrete subgroup SL2Z acting on the upper half plane. So for any gamma in SL2Z and Z in the upper half plane, f of gamma dot C. So f of gamma dot C is basically AZ plus B over CZ plus D. So that f of AZ plus B over CZ plus D is equal to CZ plus D to the K times f of Z. So here K, this K is giving you the weight. So this is the weight.
Anirudh, level 1 is good enough for the whole theory, or we go to other
No,
levels
just
on?
I think for now, it's good enough. Yes. In this, it's probably good enough.
Okay.
Yeah. So the first thing is this, the fact that it behaves well with respect to the action of the upper half plane, action of the SL2Z on the upper half plane. And the second is something called as like the boundedness when you go to infinity. So this limit as y tends to infinity f of iy should exist. So um, so if it exists, it's it's called as a modular form of weight k. If it exists and it is equal to 0, then it is a special form called as a cusp form. Okay, so one thing to note is that there are no odd weight modular forms, and this can be seen because this matrix belongs to SL2Z, and if I use the first property, I get f of negative z, uh, or f of z is equal to negative z to the k, sorry, negative 1 to the k times f of z. So if k is odd, then f should be 0. So if I want to look at non-trivial modular forms, I have to have weight even. So I have to have even weight.
Yeah.
Okay. So one um, interesting perspective to look at modular form is the geometric perspective when we look at the quotient of the upper half plane using SL2Z. So if we did the same thing using SL2R, we'll get something very bad. But if we do, since we're modeling out by SL2Z, we'll get something nice, and it is going to have a fundamental domain like this. So we can think of this as a punctured disk, and um, topologically. So when you want to look at, so this has a
What do you mean by gamma 1? Is that gamma 1 or y 1? What
y1.
is
I'm just
why?
denoting by y1.
You're
Yes.
denoting it. Okay. Okay.
It's usually denoted by y. So level n is denoted by yn or y naught n,
Mm-hmm.
things like
Okay.
that. So holomorphic model function f is a modular form of weight k if and only if I look at f dz to the k over 2, this is an invariant SL2G invariant differential on this space. So, and it basically says that if I have f of gamma z, d of gamma z to the k over 2, this I have to get f of z dz. I'm going to get an equality of this. And this happens if and only if f is a modular form of weight k. So I guess later on, many people sometimes just work with this definition of um, model form being like a differential on a modular curve. But we don't need to look into that. But this is just like a side note where we can see why the geometry is okay. So one important thing associated with modular forms is the Q series, where if I have a modular form f of weight k, so note that this matrix 1101, so the transition matrix is in SL2Z. So for all z in the upper half plane, we have f of z plus 1 should be equal to f of z, just by using the property 1 of the definition of modular form. So any modular form, it will in turn be a periodic function. So now using Fourier analysis or complex analysis, we get the following power series in Q. So in this case, Q is a specific function on Z. It's the exponential of 2 pi iz. So when Q is the exponential of 2 pi iz, f of z is given by summation afn q to the n, where n varies from 0 to infinity. So for every modular form, I have this power series, and this af0, which is the constant term, this is exactly the limit of f of iy, where y tends to infinity. And we with from our definition we saw that this was finite. And if this was 0, so that's af is 0 if and only if f is a cusp form. And these AFNs are called as the Fourier coefficients of the model form F. So we should think of model form as very much given by this data. So every model form will correspond to this data uniquely.
So you are viewing it as a periodic function and you're calculating the Fourier coefficients.
Yes, yeah. Yeah. So we look at the first interesting number theory example of a modular form, and it is given by something called as an Eisenstein series. So it is defined as the sum over mz plus n to the power of negative k, where m comma n are integers, but both of them cannot be zero simultaneously. So if I think of uh, think of the complex plane, and if I think of the say a lattice in the complex plane, uh, so this is basically adding, say, taking points on a certain lattice, and then so they are complex numbers, taking their negative power, kth power, and then summing over everything. So if you like using just analysis, it will converge whenever k is at least 4. So this function, which is defined in this manner, will give us a modular form of weight k and level 1. and this is called as the Eisenstein series, or yeah, this is called as the Eisenstein series. And this is the first example of a model form you'll see in any course on model form. So one interesting thing is its Fourier expansion, where we see the zeta function, the Riemann zeta function arise, and the divisor function, the generalized divisor function. So here sigma k minus 1 of n is, as we saw before, d to the k minus 1, where d divides n. So the k minus 1th power of the sum of the k minus 1th powers of the divisors of n. So the everything here is very number theoretic in nature, and that's why this plays a very crucial role in this theory. So zeta k is a Riemann zeta function.
Yeah, who
The
saw this connection between Eisenstein series and the Riemann zeta function?
I think no, like it just it's pretty easy to see this. Like it is not. It is just a fact that okay, the reason why Einstein series is important to number theory is because the if you just look at try to find its Q series expansion, you'll see the zeta function and this divisor function arise.
Okay.
Yeah. Okay. Um so here zeta s is the Riemann zeta function, which is analytically continued to the whole complex plane, a metamorphically continued to the whole complex plane with a pole at 1. So here zeta of 1 minus k is we know what it is because um, like we know what it is if we know the value of zeta of k. So by the functional equation. Okay. So basically, so we have this Eisenstein series, but we want to make it better. So we divide by certain constants to get our new Eisenstein series ek, where it is just this constant times gk, so that the power series, the Q expansion looks like this simple form, zeta 1 minus k over 2 plus the summation sigma k minus 1 of n q to the n. So, so this part is, you see that this zeta 1 minus k is like a special value of the zeta function. Is the value of a zeta function at a special point, like 1 minus k. So and people study special values of such L functions or zeta functions. And when k is 12, zeta of negative 11 is equal to 691 over 16380. And this 691, you see where 691 arises now. So 691 arises as as a constant term of the 12th like the weight 12 Eisenstein series. So it divides the constant term of this weight 12 Einstein series. Okay. So we see 691 now. Now we want to look at how do we realize the tau function? And as Ramanujan already did it, it comes from a modular form, which is the first, which is also the first non-zero cusp form you'll see is a Ramanujan delta function, which is basically you can think of it has a different definition, but you can just define this to be uh, the with the Q series which we had before, you can just define that to be the Q series of this function, and it will define a modular form of a cusp form of weight 12. And it'll be a cusp form because it's the Fourier expansion or the Q series expansion starts from n equal to 1. So the constant term is 0. Okay. So one important fact is due to this geometric fact called the Riemann-Roch theorem, uh, which says that any modular form of, which doesn't say, but it's a consequence of that. Uh, any modular form of weight 12 is of the form is a linear combination of E12 and delta. And in particular, if I have a cusp form, it will be a scalar multiple of delta. So a cusp form of weight 12 is always a scalar multiple of delta.
Okay. Any modular form can be written in this form. Okay.
Like any modular form of weight 12.
Okay. This cusp form is related to the Eisenstein series, right?
No, cusp form is related to delta, and the other thing is the Eisenstein series. So Eisenstein series is like the
Ah,
disjoint of cusp form.
okay, 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 okay.
Yeah. So if I look at modular forms of weight 12, this is now this Einstein series plus cusp, and they don't have any intersection. So it's like so that's why we have this. So it's a if I look at the space of modular forms of weight 12, then it'll be a sum of an Einstein series and a cusp form. That's what I'm trying to say.
Okay.
And here in this case, the cusp form, the specific cusp form is delta. So I have that. So mainly I want to what I'm saying is is the dimension of weight 12 modular forms is just 2. It's a two-dimensional complex vector space. And this dimension is where the Riemann doc is coming to picture. Where the Riemann doc talks about the dimensions of these vector spaces. And then using Riemann doc, I know that this is two-dimensional. And I already have two things. There are 12, the 12, weight 12 existences and the Ramanujan delta function. And I can't have any other thing. So every other thing should be a linear combination of these two.
So you are essentially talking about the vector space formed by a
Yeah.
collection of all modular forms of weight 12.
Yes.
Okay.
Yes. Yeah.
Oversync. Okay.
Yeah, I can also look at over Q as well, but yeah, okay. Uh, Fine. Okay, so now we have two things. So we have this delta function, we have the weight 12 Eisenstein series, and we now know where 691 comes into picture. So now we talk about congruences. So the tau n, which is the Fourier coefficient of delta n or delta z, and sigma 11n, which is the Fourier coefficient of E12, they are all integers. So when you have and moreover, this constant term is a 691 adic integer. So what do I mean by that? It just means that 691, the denominator, so this part has nothing to do with 691. So it's co-prime to the prime 691. So I can talk about divisibility in the ring. Uh, so I can talk about divisibility in the ring Z691. So Z691 is the ring of 691 adic integers. You can also think of this as the ring Z localized at the prime ideal 691. So it's all the rational numbers where um, it's all the rational numbers where 691 does not divide B. So that's what I mean by that. So we can think of so when we are looking at congruences, we are looking at congruences in this way.
Otherwise, you are realizing it in a periodic field.
I can, but yes, there.
Essentially.
I yeah I would want to do that sometimes when yeah. I don't think I need to do it here, but
Yeah.
I can. Okay, so so using this, so this is an important note to keep in mind. So, but before going further, we define what do we mean by the two model forms to be congruent. So, two model forms are congruent when the Fourier coefficients are congruent, or the QX, the Fourier coefficients AF AFN and AGN are congruent modular prime P. So if I have two model forms F comma G of weight K with integer non-zero coefficient, integer non-constant coefficients. Um, so integer non-constant coefficients meaning that AFN and AGN are integers for all natural numbers n. So we say that F and G are congruent modulo prime P if AFN is congruent to AGN mod P for every n greater than or equal to 1. So we write F congruent to G mod P in that case. So two model forms are congruent if and only if their Fourier coefficients are congruent. Okay. So we can now think where this might, the main question of Ramanujan's congruences. Ah, wait, this congruence. So this is the Fourier coefficient of the delta function. This is the Fourier coefficient of the Einstein series of weight 12, and 691 is the prime dividing the special value. So basically, what we are trying to now show is that the weight 12, the Ramanujan delta function is congruent to uh, the weight 12 Einstein series mod P mod 691. So we show that delta is congruent to mod 690. So such a congruence of a cusp form, in this case, like delta is a special cusp form, which I'll talk later. So delta is congruent to an Einstein series mod a prime. So in this case, it's 691. So such a congruence is called as an Einstein congruence. And I think my last slide will just be to say that where these kind of congruences are used. Okay. So now to show that delta is congruent to the Einstein series, we now show that there is at least one cusp form of weight 12 with integer coefficients and whose first term, first Fourier coefficient is 1, that is congruent to the Einstein series mod 691. So we just construct a cusp form, and from a fact we'll show that this cusp form should be equal to the delta. So consider the weight 12 modular form G prime, which is this some constant 240 times E4. E4 is the weight for Einstein series, and you cube that. So when you cube a weight 4 Einstein series, the weight becomes the multiple 3 times 4, which is 12. So now this will be a weight 12 thing. Uh, this is the weight 12 thing. And now it will be a weight 12 with some constant term. And 240 is chosen such that if I look at the constant term, I'm going to just get 1. So using this, I just change the Einstein series by this constant. So now this will be a cusp form because of by our choice. So if I look at AG of 0, it'll be AE12 of 0 minus zeta negative 11 by 2. It is zeta negative 11 by 2 minus zeta negative 11 by 2. See, so I'm choosing this constant term to make sure that G is a cusp form. That's what I'm doing. So G is now a cusp form of weight 12 with integer coefficients. And if I look at 691, 691 divides zeta of negative 11. So now modulo 691, this becomes 0. So thus I have this congruence G congruent to E12 mod 690. Does that make sense?
Yeah.
Okay. Okay. So we have done the first step where we found a cusp form with integer coefficients, which was congruent to the Einstein series mod 691. And now we just have to show the other part where I want the Ramanujan delta function to be congruent to E12. And to do this, we know that this cusp G should be a multiple of delta, and by our construction of G, the first term, the first Fourier terms coefficients are both 1. And we know that the delta term, the tau of 1 is also 1. So hence A should be 1. So if A is 1, then G should be delta. So it's just straightforward in this case. So this proves the Ramanujan's congruence, where this congruence of modular forms is giving us this congruence of arithmetic functions. So you can um, like, this is a very good way to produce congruences of certain interesting um, arithmetic functions, just if like coming from modular forms.
So from where did Ramanujan see this problem to work on?
I think I don't know. He just found the uh, I think he did not use this method to prove this at least, but he had used some other um, elementary techniques to prove this. But I'm not sure actually.
I
I've
think
not checked.
Hecka didn't come to the scene yet when Ramanujan
No,
was
no,
working, right?
no, no. Yeah, heck operators
Okay.
and everything they were not. Yeah. So this delta is actually some. So there are these Hecke operators which act. There are these special linear operators which act in space of modular forms, and these del. So there are a sequence of operators for every integer n, and the delta and the Einstein series, both of them, they are like eigenforms for those operators. So this congruence is special in the case in the sense that delta is now an eigenform, which is congruent to an Einstein series modular prime. And this is very important in the general theory.
Yeah, so
So
this is algebraic thinking, but
yeah,
one says that Ramanujan was thinking in analytic fashion rather than an
yeah,
algebraic fashion.
yes, yes. I think yeah, he was more analytical. Yes,
Okay,
yeah,
what is that ribbit connection you have?
yes. So the last slide is just like a note on something called as Ribet's method, which also what I'm interested in is just using these Einstein congruences. So Eisenstein congruences is a congruences of certain Eisenstein series with a cuspidal eigenform uh, for the Hecke operators, modulo certain prime, modulo prime P. And Ribet actually in this breakthrough paper in 76, so it's the paper is called a modular construction of unramified P extensions of Q's mu P. So this is just a 10-page paper, but it has influenced a lot of mathematics. Um, so he produces an unramified extension of uh, P cyclotomic field Q zeta P, where zeta P is a primitive P root of unity. And these in turn, so he used this to prove something called as a converse to Herbrand's theorem, which I've not specified, but it is a very interesting result about class groups and p-density of certain class groups. But the method is so is just using such an Einstein congruence and uh, and to proceed further. So this method of using Einstein congruences or to is also has been generalized by Wiles and Maser-Wiles uh, in the early 80s and 90s to prove certain results in Iwasawa theory and mainly to prove the main conjecture of Iwasawa theory. And now people study like these things in the context of this uh, like this main conjecture called as the Bloch-Carter conjecture. And this method of producing um, so yeah, Ribet's method is somehow starts on this Einstein congruences, but it has found its way to like to answer much more interesting and deep questions. But yeah, that was the
Hmm,
main thing
nice.
I wanted to say.
Yeah.
Yeah.
So, but you mentioned Delhi. Did this exposition touch upon what were the methods of Delhi?
No, I have not told anything about what Delhi did, but because I don't know anything about what he did.
But for the fact that this arises in his Fields Medal winning work.
Yeah, yeah.
Yeah. And then your Iwasawa theory is something to do with class field theory.
Yes, it's like it's studying class fields in like extensions of so class groups, just not just a class group of a number field, but set like class groups of in an extension or like
Galva
how they
extension.
vary. Yeah, like a ZP extension. So look at something called as a an infinite Galois extension of say a base field, and then and your Galois group you want it to be like ZP, and you have these like finite parts, and you look at the growth of the class group in these finite parts. And moreover, this class group, the whole thing, you'll get something called as a lambda module structure. Here, lambda is like a power series in one variable, and this lambda module structure will give you some invariant. And this invariant, like this, not an invariant, but it'll give you some ideal, like a cat called as a characteristic ideal. And this characteristic ideal is generated by a um, the conjecture is that this characteristic ideal is generated by something called as the like a periodic L function. So this Iwasawa theory basically relates this characteristic ideal of certain algebraic thing to periodic L functions, which are analytic in nature. So Iwasawa theory is a bridge in that sense.
Okay.
Yeah,
Nice. Thanks for the wonderful lecture.
yeah, no problem, sir.
Yep. Okay. We'll, yeah. Thank you.
Okay,
On behalf of Jain University Math Club, I would like to thank for the wonderful lecture, and we'll end the session now.
thanks.